For decades, the personal computer relied on a divided workforce. Under the hood, your CPU and GPU sit on opposite sides of a sprawling motherboard. To complete a heavy task, they must constantly ferry data across a PCIe bus. But that geographical divide becomes a bottleneck the moment you try to run massive, 100 billion parameter AI models directly on your desk. Moving datasets that large across a physical bridge creates immense latency. It chokes the system, rapidly burns power, and stalls the operation. The traditional discrete architecture is not designed for the bandwidth required by an always-on, local AI agent. The hardware itself had to be rebuilt at the silicon level. To solve this data traffic jam, Nvidia engineered the RTX Spark. They shifted away from the traditional x86 framework in favor of an ARM-based system-on-chip. Instead of separate components, they fused a custom Grace CPU, a Blackwell GPU, and 128 gigabytes of memory onto a single piece of silicon. By condensing the hardware, the thermal and spatial footprints shrink, allowing this entire array to fit comfortably inside a laptop chassis just 14 millimeters thick. While this setup powers ultra-thin Windows consumer devices, the same silicon architecture drives Nvidia's professional desktop appliance, the DGX Spark, aimed at data scientists. The compute density is significant. The internal Blackwell GPU packs over 6,000 CUDA cores, generating a full petaflop of AI processing power. Shrinking this much processing power into a compact mobile chassis depends on this level of tight physical integration. ARM architecture has become an industry standard for maximizing performance while keeping power consumption low in personal computing. But Nvidia's implementation eliminates the latency found in older designs. By utilizing NVLink interconnects, they bypass legacy PCIe bottlenecks, bridging the GPU directly with a custom 20-core Grace CPU, built in partnership with MediaTek. The consumer market has already seen this logic succeed. Apple Silicon showed that unified memory and ARM design could yield massive performance gains in laptops. Nvidia is leveraging that baseline, adapting it to deploy their dominant CUDA software ecosystem into everyday personal computers. Under the hood, those MediaTek-designed Cortex X925 CPU cores are etched using TSMC's 3-nanometer manufacturing process. By building around this architecture, Nvidia is positioning high-performance ARM as a primary focus for its future consumer software efforts. Looking at raw specifications, a professional might assume a massive discrete desktop GPU, like an RTX 5080, would outpace a 14mm laptop in AI tasks. This chart shows where that assumption breaks down. High-end consumer desktop cards typically hit a hard VRAM ceiling between 16 and 24 gigabytes. If you try to load a dense 120 billion parameter large language model, the data footprint is so massive it overflows that discrete memory pool. It physically cannot fit. The RTX Spark avoids this limit by pooling resources. The GPU dynamically pulls from the 128 gigabytes of unified system memory to hold the entire model at once. Because the CPU and GPU share the same memory yard, data never has to be ferried across a motherboard bridge. Access is instantaneous. Reaching 128 gigabytes of VRAM with traditional hardware requires multiple expensive, heat-generating discrete cards in a server rack. Here it sits on one chip. This unified memory architecture provides the necessary data handling framework for running large-scale AI models within a mobile device's power and space constraints. Exceptional hardware sits idle without an operating system equipped to use it. The enterprise software ecosystem had to adapt.
In collaboration with Microsoft, Windows on ARM utilizes the Prism translation layer, allowing legacy x86 applications to run on the new architecture without the user needing to manually configure them. Because mobile phones and data centers have run on ARM for years, developers already have the tools to compile their software natively for this environment. This flowchart maps out the resulting workflow. In partnerships with Adobe, heavy applications like Premiere Pro can tap into the unified memory pool, eliminating the need to duplicate video files between system RAM and the graphics card. The performance gains are tangible. Adobe Photoshop, for example, is reportedly reaching 100% GPU acceleration. Multiple demanding applications and background AI agents can execute overlapping instructions simultaneously, drawing from the same pool of resources without friction. Hardware integration provides the runway, but the actual speed comes from rewriting software pipelines to eliminate redundant data duplication. Historically, ARM processors have struggled with heavy graphical workloads, leaving gamers skeptical of the architecture. This chart illustrates how that narrative is shifting. An emulated game like Pragmata yields 40 to 50 FPS. Translated titles like Alan Wake push past 60 FPS. When compiled natively for ARM, like Fortnite, frame rates easily clear 100 to 120 FPS. Nvidia accelerates this performance by embedding their Blackwell architecture into the chip, bringing DLSS and ray reconstruction natively to the ARM ecosystem. By utilizing AI to generate intermediate frames and upscale resolution, the GPU delivers high-fidelity rendering while staying within a 50 to 100-watt mobile power budget. Real-time rendering is computationally expensive. AI upscaling bridges the performance gap, allowing an ARM device to output top-tier graphics without exhausting the battery. All of this hardware and software optimization serves one primary function: running AI agents continuously in the background of your workflow. Asking an AI to analyze your tax documents or private company code currently requires transmitting that sensitive data to external cloud servers, a risk for enterprise users. This schematic breaks down the solution. Nvidia's OpenShell creates a strict identity containment layer on the machine. It acts as a traffic controller, routing sensitive queries to the local model securely, while utilizing the cloud for generic tasks. Third-party developers are already integrating this logic. AI agents like Hermes and OpenClaw have committed to adopting these exact Windows privacy layers. If a complex query must be sent out to a cloud model, OpenShell acts as a failsafe, automatically stripping or disguising personal information before it leaves your local network. For privacy-conscious individuals, keeping data sandbox contained is a primary way to safely integrate powerful AI assistants. The dependency on discrete x86 components for high-performance daily computing is beginning to fade. The hardware itself is adapting. The computer is shifting from a static terminal into an active collaborator that reasons through tasks alongside you. Maintaining that constant intelligence directly on your device requires specific physical infrastructure. It relies on the low-latency integration of Grace CPU cores, a Blackwell GPU, and 128 GB of unified memory. The machine on your desk is being rebuilt as an intelligent, secure, local reasoning engine. Nvidia's RTX Spark represents a response to this requirement. It provides the architectural foundation necessary to power continuous, local AI.